All right, welcome to part 2 of Igneous Rocks. So at the beginning, I asked you this question. All of these are igneous rocks, however, they have very different colors and textures. So how can we use the color and texture to hypothesize the difference in formation conditions? In the first half, we talked about formation conditions, but we haven't yet related that to color and texture. So in the second half, that's exactly what we're going to try and do. Figure out how color and texture tells us something about the formation conditions. We're also going to dive into a little bit of a case study on the Yellowstone hotspot. All right, so we talked about rock textures yesterday with sedimentary rocks, and there we were talking about the size of the grains that made up sedimentary rocks, and we were talking about bedding. With igneous rock textures, we're going to be talking mostly about the crystal size. And just to really emphasize that difference between igneous and sedimentary rocks, both of them are made up of smaller pieces. In terms of sedimentary rocks, they're made up of other smaller pieces of other rocks. And in igneous rocks, they're made up of minerals. And while in sedimentary rocks, those other rocks needed to be bound together by a cement between each grain, igneous rocks are bound together because the crystals grow in an interlocking structure, much like a puzzle piece, except it would be in 3 dimensions, and so very strongly locked together. And this third panel just shows if you expanded each of those grains to a separate piece, you can see exactly how interlocked those crystalline igneous rocks are compared to the sedimentary rocks. We're going to talk about a few different rock textures here. So just to give you a heads up about this jargon, and then we'll go through each of these in more detail. When we talk about texture, we're going to talk about glassy, like you see in this image, aphanitic, phaneritic, and porphyritic with phenocrysts. So in igneous rocks, we are a great fan of those pH words. We're going to use these different textures to identify how the magma cooled. This is going to give us some clues as to the rate of magma cooling and whether that magma cooled on the surface as an eruption or below the ground as a magma chamber or a dike or a sill. So we'll start out with glassy rocks. Glassy igneous rocks, you might think that they have very, very small crystals, but it turns out they're actually acrystalline. And they form through an extremely rapid cooling of magma, which creates unordered molecules that do not result in any sort of ordered crystalline structure. So this unordered nature of it is what leads to an acrystalline form. Because they're forming through very, very rapid cooling, they tend to form in eruptions. They have very similar properties to window glass in terms of how they break because of this acrystalline structure to them. So they have conchoidal fractures, and that's what you can see in all of these images. These kind of circular breaks are conchoidal fractures, much like you'd see if you broke a large chunk of glass. They also would be about the same color as window glass normally, so kind of clear, except for the fact that in the formation of these glassy rocks, we tend to get a little bit of iron and magnesium, just a small trace amount, and that can significantly change the color. So we're more used to seeing these glassy rocks as obsidian that's black, but it can also have strands of orange in it as well as some other colors. So what kind of environment would allow for this extremely rapid cooling of magma? I sort of answered this question on accident earlier. We tend to see these with volcanic eruptions and usually very explosive ones associated with stratovolcanoes, because in that instance, you have magma rapidly being ejected into the air and rapidly subjected to cooling. The next texture here is going to get us into a crystalline form. This is aphanitic. Aphanitic igneous rocks have fine-grained crystals. They're generally fine enough that you can't see individual crystals with your naked eye. You can tell that there is some crystal structure, and if you had a magnifying glass like a hand lens, so a handheld magnifying glass, you would be able to start to see those crystals under magnification. These are going to form through relatively fast cooling in volcanic eruptions. So the fast cooling is necessary for small crystal sizes because everything is cooling all at once and you don't have the time that's necessary for crystals to grow to a large size. So the crystal size is going to relate a lot to how much time was available for those crystals to grow larger and that growth rate to increase. These aphanitic rocks, because they form through fast cooling and volcanic eruptions, are often called volcanic rocks, which just lumps the rock name with the origin of the rock. So some examples here of common aphanitic rocks include rhyolites and basalts. We'll talk more about the composition of these to get their actual name, but you may have heard basalt as a fairly common rock name. If we move up in crystal size, we get to phaneritic rocks, and these are going to be coarse-grained. So this means you can see the crystals with your eye, and in fact, these crystals can be fairly sizable on the scale of centimeters. They form through slow cooling below the Earth's surface, so these are going to be rocks that are in magma chambers that slowly cool at depth. And because they are slowly cooling, there's a lot of time for the crystals to grow larger in size. They are often also referred to as plutonic rocks because they're forming below ground in magma bodies that are known as plutons. Some examples of phaneritic rocks include gabbro. So you may see gabbro in places like Hawaii or old ocean crust. And then, of course, ubiquitous to us here in Colorado Springs is the Pikes Peak granite, which is a phaneritic igneous rock, specifically a rock type called granite. And you may have noticed if you pick up a piece of granite, you can see a lot of those interlocking crystals very visibly with your naked eye. So these kind of darker black hornblends and the lighter feldspars. Okay, and then the last texture that we'll go over, again, in love with the pH combination in these words, are porphyritic rocks that contain phenocrysts. This essentially is a rock with two grain sizes. So you have larger crystals, which are called phenocrysts, and then you have a smaller ground mass, which surrounds those larger crystals. So in this example in the upper right, these white blobs are phenocrysts. They've been cut with a saw, so that's why they're very smooth here. These are the phenocrysts. And then this gray area between each of these phenocrysts is the ground mass. In this example, the ground mass is fine-grained aphanitic, but you can also have examples of porphyritic rocks where the ground mass is actually phaneritic. So here's an example on the bottom right where the pink feldspars are going to be the phenocrysts, and they are surrounded by this black and white ground mass, which has visible crystals. However, the crystals are significantly smaller in size. So we talked about slow rates of cooling and fast rates of cooling earlier. So what rate of cooling could cause porphyritic textures? So take a second and think about this. And when you think you have an answer, move on in the lecture. All right, so porphyritic textures are going to result from two-stage cooling. So we initially have a slow cooling below the ground surface, and that's going to allow the phenocrysts, or the larger crystals, to form. If you remember, larger crystals are associated with slow cooling rates, which means we can't be exposed to air because air is going to cause fast cooling rates simply because of that heat difference. So these phenocrysts are formed usually below ground, and then the magma that contains these phenocrysts might be erupted. And as it erupts, it's suddenly subject to a much higher temperature difference, which leads to a rapid cooling rate and forms the smaller ground mass, which surrounds the phenocrysts. All right, so I want to go over one more texture on the scale of minerals, and then we'll try and apply this to a case study in Yellowstone. So we talked about the two-stage cooling process on the scale of mineral sizes. However, if we look within a mineral, we can also see evidence of this. So what we're looking at here is an amphibole. which is a type of mineral. And we're looking at it in polarized light under a microscope. So we've basically taken a rock, cut it away into a very thin section and put it under a microscope. And we're able to look kind of backlit at all of the minerals in that rock. And each of these minerals has slightly different optical properties that allow us to identify it under a microscope. So what we see here is this amphibole, and it has this black ring around it, and then a brown amphibole crystal. So the brown crystal is the original, or is what is still amphibole. However, around it, this black rind around it, is where the amphibole crystal used to be. And so it's being replaced as the magma depressurizes and rises. And those new pressure conditions, the new composition within the magma allows new chemical reactions to occur on the boundary of this crystal. And so we can use these kind of textures within the crystals themselves to tell us something about how the conditions might be changing of the melt. Usually in the case of, is pressure and temperature changing, or are we getting a new composition? Right, so another example of this is zoning. Here we're looking at one mineral outlined in gray, but within the mineral, it has all of these alternating light and dark bands. And these are called zoning bands. And so it essentially shows that as this mineral grew from its original position outward, the composition of the magma that it was incorporating was slightly different throughout time. And so it was creating these slightly different composition bands within the crystal as it grew. These could be changed, or so never mind, the composition is not changing, sorry, but the reaction rate is changing. The composition changed, we would see a different mineral. So what these zoning bands are showing us is a change in the reaction rate as that mineral is growing outward. And the reaction rate is going to be dictated by the temperature of the magma or a slight change in the composition of the magma. On the bottom, we can see another example of these zoning bands. In this case, there's kind of just one inner zone and then one outer zone, rather than this kind of back and forth alternation that the upper one shows. Okay, so now let's see if we can apply this to understand how the Yellowstone hotspot erupts. So the Yellowstone hotspot is, if you read the wrong news sources, is often sensationalized as the next big disaster. There's one particular, I don't want to call it a newspaper, but a magazine that every month or two just decides that Yellowstone is going to erupt and starts publishing articles about how the world is going to end soon. That's not really where we're at. And we can use the rock textures and these mineral textures to actually figure out, is that a realistic prediction, or is this magazine just spouting nonsense? A little bit of background on the Yellowstone hotspot. So on the right here, you can see the states. We've got Oregon, Idaho, Montana, and Wyoming. The current Yellowstone hotspot in Yellowstone National Park is in the northwest corner of Wyoming. And each of these blobs represents an eruption of the Yellowstone hotspot and some volcanic rocks associated with it. And then their age in millions of years ago is shown within each blob. So you can see that about 16 million years ago, the Yellowstone hotspot was in the northwest corner of Nevada. Since then, it has traversed across Idaho. It left behind the Craters of the Moon National Monument, and it has now reached its current position. Now, when I say the Yellowstone hotspot has traversed, what I really mean is the Yellowstone hotspot has remained stationary, but the North American plate has moved across it in this direction, so towards the older hotspot tracks. And we can use rocks from the recent Yellowstone eruptions to try and figure out how those eruptions proceeded and whether or not they represent significant hazards. So we're going to be looking at some data from a recent study that looked at the Summit Lake flow of the Yellowstone hotspot. And The Summit Lake flow erupted about 124,000 years ago. We can use the rock textures within this flow to say something about how it erupted. And so in this next slide, we can do that. These are the rock textures that we see from the Summit Lake flow. They're fairly light in color, and compositionally, we know that they are felsic. They have a lot of silica, oxygen, aluminum, and potassium in them. And then if we look at the textures of them, how would you classify the texture of these rocks? Are they aphanitic, phaneritic, porphyritic? So keep that in mind and think about what would that indicate about the rate of cooling. And then we can also look at the mineral textures within these rocks. So if we were to kind of take out one of these larger phenocrysts from these rocks and look at it under thin section, we see textures that look like this. So this is that zoning that we talked about, where as the crystal grew outward, it experienced some changes in the temperature or pressure of the surrounding magma melt, or a slight change in the composition that resulted in some zoning as that crystal continued to grow larger, right? And what this particular microscope is showing us, the darker areas tend to have lower amounts of titanium, and the lighter areas have higher amounts of titanium. And these relate to temperatures. So we know through previous literature that low amounts of titanium indicate lower temperatures. So these dark areas have low temperatures or lower temperatures, and the light areas tend to have higher temperatures, right? So kind of the center of these minerals. So what does this tell us about how temperatures may have changed over time? Kind of up to you for your own interpretation, but now that you've looked at mineral textures, you've looked at rock textures, and hopefully you have some sort of hypothesis in mind, let's check that against what the original researchers found. And we'll just note that they had access to a lot more analytical tools than we did, so they were able to look at this in a little bit more detail. But they found that the rock type is rhyolite, that's that felsic rock, and they have the potential to be very explosive because they are felsic and therefore more viscous and resistant to flow. However, when they looked at the minerals and the zoning in the minerals, they found that it looked like there were two stages to this, where two magma bodies were combining. And that's why we get that zoning in the titanium from light to dark titanium from the center to the outside of these phenocrysts. And they were able to actually back this out with some numerical modeling to say that that occurred at a timescale of 2 to 5 years. So that combination of magmatic bodies over 2 to 5 years overpressured the magma chamber, and this triggered an eruption of the lava. So if you remember from the rock textures, we had those large phenocrysts, but we also had some fairly fine-grained rocks that indicates there must have been a surface eruption component. When they looked at these rocks and combined this with temperature modeling, they found that even though the magma chamber was overpressured, the eruption that occurred was actually effusive and non-explosive. And it mostly occurred through vents that surrounded the main volcanic edifice. So instead of being a centralized eruption, it was more of an effusive eruption through vents and fissures. So that's pretty cool. That's a lot of information that we can get out of just looking at the textures of rocks and the textures of minerals, and then combining that with some temperature modeling. So after that case study, I'd like to then go into how we actually name these rocks and what their compositions are. So before we assign names, we need to understand where they came from, which is something that comes from the composition, right? So the first half of this, we talked about how that composition changes with plate tectonics and with the magma path up to the surface. So for example, the granites and gabbros shown here, granite on the left and gabbro on the right. These are both phaneritic textures, but we would never expect them to form together because their compositions are so different. So one of these is mafic and one is felsic. And we may expect to see them with some bimodal volcanism from continental hotspots. However, it is really uncommon to see these. So we'll talk about igneous rock composition now, and think about how the temperatures change through the Earth. So as we start from the center of the Earth in the core to the surface, as pressures are decreasing and we get away from any sort of radioactive heat generated in the core, the temperature is going to decrease. However, it doesn't decrease in a linear fashion. Instead, we see kind of these jumps that often have to do with compositional bounds. So at the boundary between the core and the mantle, the temperature suddenly decreases. However, note it's still pretty hot at 3000 degrees Celsius. And then throughout the mantle, the temperature continues to decrease until we reach the asthenosphere and lithospheric boundaries, where temperatures decrease but at a different rate. And when we're very close to the surface, this rate of decrease is about 30 degrees Celsius per kilometer. So as the magma rises another kilometer towards the surface, it tends to lose 30 degrees of temperature. And we've just blown up what this top part looks like from about 0 to 500 kilometers depth, just to show that in more detail. So this is just to preface the actual rock compositions and the minerals that are forming at different temperatures. So this is a fairly well-known diagram called Bowen's reaction series, and it is a really nice conceptual diagram to think about what mineral assemblages and what colors are associated with different temperatures. So at the top at high temperatures, we tend to get rocks or minerals like olivine and pyroxene and calcium-rich feldspars crystallizing out. The colors here are kind of represent the colors of the minerals themselves. So you can see this is kind of a darker greenish assemblage of minerals. And as temperatures continue to decrease, so getting closer and closer to the surface, we tend to see amphiboles, biotite micas, things that are black or gray in color. And as we get into the lowest temperatures, we have potassium feldspar or K-spar, which is pink, and that's the mineral that makes up the pink rock of a lot of Pikes Peak. We get muscovite and quartz, so kind of white to pink assemblages at very low temperatures. If we actually try and put numbers to these temperatures, we see that olivine tends to crystallize at about 1400 degrees Celsius. Let's think about what depth that is. And then we can do the same thing with quartz, which starts to crystallize at about 800 degrees Celsius. So if we use the assumption of a 30 degree Celsius per kilometer gradient, we would calculate that, this is olivine is starting to crystallize at about 100 kilometers depth, which is close to where the lithosphere-asthenosphere boundary is. And this matches with where we see a lot of olivine. We tend to see it on the bottom of tectonic plates. So in instances where plates collide and actually scrape off a cross-section of themselves, we see olivine closer to the bottom of that cross-section. And then quartz is going to start to crystallize at much lower depths, about 50 kilometers. And this makes sense. We see a lot of quartz in continental rock. And so 50 kilometers is right in that range where we have continental crust. And these are going to tie into the composition of rocks. So we're going to call rocks that tend to be enriched in olivine and kind of this green color ultramafic, right? So we talked about mafic earlier as being very iron and magnesium rich rock. And ultramafic rock is going to be like a direct from mantle source. So ultramafic rocks, think of this as being synonymous with mantle rock. As we get a little bit darker in color, so we may still contain a little bit of olivine, but mostly pyroxenes and amphiboles and calcium feldspars, we tend to get rocks that are dark in color, gray to blackish, and these are mafic rocks. Intermediate rocks tend to be a lighter color, so they may be black and white, not yellow, but kind of black and white colors. And then our felsic rocks at the lowest temperatures are going to contain pink feldspars, and then also a lot of white quartz. So they're going to be fairly light in color. So even though we are in a remote classroom right now, we don't have the opportunity to necessarily look closely at the mineral composition. We can use the overall color of igneous rocks to tell something about what the composition is and to inform what minerals we would expect to see if we were able to look at them in more detail. So just to drive that home, we can, without necessarily knowing all the minerals, we can still identify the composition, and we can still back out something about the formation depths and formation temperatures of igneous rocks. So let's try that out. Based on the color and texture of this rock, how did it form? So I would recommend pausing for a couple seconds, thinking about what your answer for this would be, and then unpausing when you're ready to continue. All right, so what did we have for texture? Texture here is going to be phaneritic, right? So it's coarse grained. We can see the individual crystals. And what about the color? The color is green. It's very dark. So how did this form? Well, we assume based on the texture that it cooled at depth. Based on the color, we can say it's a mafic or ultramafic composition, which meant it had to be a fairly hot magma that cooled. And then it formed near a mafic source. So we could see this cooling at depth within a hotspot magma chamber, or we could see it associated with a divergent boundary when we have magmatic mafic magmas rising to the surface and some cooling occurring before those magmas reach the surface, right? So I wrote over this on accident, but this is kind of, as we said earlier, it's formed at depth in the earth, likely near that asthenosphere-lithosphere boundary, and through a process of slow cooling. All right, let's try this again with this rock. So again, take a couple minutes, think about the color and texture of this rock, and hypothesize how it formed, what temperatures and what rates, and what tectonic setting. All right, when you think you've got that ready to go, we'll look at least my interpretation of it. So I noted the color first. It's white, pretty pale. So that means it's felsic and formed at kind of low temperatures. I also noted that there are phenocrysts in it, so these larger rocks within a gray ground mass. And so this indicated that it is a porphyritic rock with a two-stage cooling process. So it must have cooled within the earth at some shallow depth and then erupted in a felsic magmatic eruption that likely was somewhat explosive and cooled rapidly once it erupted. Okay, so now that we've gone over the basics of texture and composition, we can move to rock naming. So igneous rocks are just going to be named based on that intersection of their composition and their texture. We'll start out with, we'll go texture by texture and then look at the compositions. So we start out with a glassy texture. Remember, this is the texture that is acrystalline, so it cools so rapidly that no crystals form. We really only have two rocks that form this way. We have obsidian, which may be what we're most familiar with. This is what arrowheads are formed of, and we may just colloquially have heard of this a little bit more. And these are felsic. So even though the rock is black, it is actually a felsic rock. The rock is due to just a very small amount of impurities like magnesium and ion that change the color of the rock. However, if you were to run this through a mass spectrometer and actually look at the the elemental composition of it, it would mostly fall into the felsic arena, where it's really dominated by silica and oxygen. We don't tend to see these rocks forming in mafic compositions or ultramafic compositions. If you remember, ultramafic is associated with the mantle, and it's going to be really hard for the mantle to erupt and cool very, very rapidly. So, but we do see some associated with mafic rocks, for example, in hotspot eruptions. And these are called scoria. They start out black, however, because they have a high amount of iron in them, they often rust through oxidation to turn reddish. And unlike obsidian, they are not glassy so much as they are extremely porous, and they have a lot of vesicles, right? So we call this specific texture vesicular. And it means that there were a lot of gas bubbles within this rock that then popped and now have left behind those gas cavities. All right, if we move on then to aphanitic rocks. So if you remember, these are rocks that are formed in fast rates of cooling, not quite as extremely fast as glassy rocks. We do see aphanitic rock textures across all compositions. However, the ultramafic rock is extremely rare. It is called comatite. And as you can see here, we see in all of these rocks that fine-grained aphanitic texture, and the comatite is going to be green. And that aligns well with the predictions from Bowen's reaction series that we made earlier. Mafic fine-grained rocks, aphanitic rocks, are called basalt. These are fairly common across lava flows in Hawaii, as well as lava flows associated with internal hotspots or vents. So across eastern Washington state and some of Oregon are basalts that cover the landscape. We also see basalts in New Mexico associated with some rifting and volcanism there. We would see these a lot in divergent boundaries. In the intermediate category, the fine-grained intermediate rocks are called andesite, and our fine-grained felsic rocks are called rhyolite. And you can see nicely here, despite the same composition, some strong color trends where we have, again, our felsic rocks that we expected to be fairly light are indeed light, and the rocks get darker in color to mafic, and then green for ultramafic. When we look at the coarse-grained rocks, we're going to see similar patterns. So the coarse-grained rocks are common in all four compositions. Under ultramafic rocks, this is going to form mostly in the mantle. We see peridotite. So this is mostly formed of the mineral olivine. And it's pretty much just a mass of olivine. And that's going to be very green. However, as the composition changes towards mafic, we keep some of the green olivine, but we start to intersperse it with pyroxenes that are a little bit darker in color. And so we get this dark, coarse-grained rock called gabbro. As we move to intermediate compositions, those coarse grains, we retain some of the black minerals, but now we add in some white minerals, and we get this black and white rock called diorite. And that rock can often look similar to granite. However, granites are often going to include a particular type of feldspar called K-spar or potassium feldspar that is characteristically pink in color. So our very felsic coarse-grained rocks will be pink and pale. Right, and then last we got our porphyritic rocks. Porphyritic rocks don't actually get their own unique name. Instead, we use a modifier to the aphanitic version of them. So a basalt that has phenocrysts within it will be called a porphyritic basalt. An andesite with phenocrysts is a porphyritic andesite, and a rhyolite with phenocrysts is a porphyritic rhyolite. And again, the color between the andesite and the rhyolite is a little hard to distinguish, but we do see a stronger pinkish hue to the rhyolite. Okay, so those are igneous rocks, the different compositions, and how we get those different compositions in relation to plate tectonics. So now I'd like you to take a sec and bring this together into one conceptual diagram to hold with you. So here we have a sketch of plate tectonic boundaries. We've got a hot spot here. We have subduction of ocean-ocean. We have subduction of ocean-continent, and we have divergence. And I would like you to think about what type of rocks would we expect at different locations. So basically take all of the rocks that we talked about in this diagram and try and place them in their correct location on this diagram. Okay, and then once you have that done, feel free to check in with me to see if you're right, to check your knowledge, or check in with a classmate. So we'll kind of leave that up and we may revisit this tomorrow morning. However, as we wrap up this lecture, I'd like to come back to this guiding question for today. So now we have these 3 rock types that we've been showing you all day. They're all igneous rocks, and we wanted you to understand the different in formation conditions based on color and texture. Well, now we actually have names for colors and textures in terms of the composition and the textures of the grain size. And so we can actually make an attempt to name these different rocks. So if we do that, this dark rock that is aphanitic is going to be a basalt. The black and white phaneritic rock is going to be a diorite. And then this black and white phaneritic rock that contains some pink crystals in it is going to be a granite. So what I'd like you to do is, for your homework, turn in that conceptual sketch related to plate tectonics that you made just 2 slides ago. And then I would also, now that we know kind of what the colors and textures represent in terms of rock names here, just double check your knowledge and think about what are the conditions under which these formed. And also feel free to revise and redraw your sketch that you're submitting, right? So just to kind of drive this home, you are submitting this sketch, but it can be revised. So it doesn't have to be what you initially come up with. And I would like you, even though it's not something you submit, I would like you to think about the answer to this question. All right, that wraps up our part 2 on igneous rocks.